Hello, my name is Pak So Kreth, and this time I am going to show you the proofs of Riemann hypothesis. I can tell you that it is a little bit long. By the way, after you watch this video, maybe you think that you think that it is easy, and some of you maybe think that it is difficult. Yeah. So let's start together. Riemann hypothesis. What does Riemann hypothesis state? Okay. Riemann hypothesis states that the non-trivial zero of zeta function, we can say Riemann zeta function, right? Zeta function are complex number whose real part is 1/2. Yeah, it means that what does Riemann say? That is every non-trivial zero of zeta function are complex number numbers whose form is 1/2 plus IB. Where I is imaginary unit and B is a real number. Yeah, it's a real number here. Is any real number. Okay. Riemann's hypothesis is developed in the mathematics and science for more than 100 of years. And he said that every non-trivial zero of zeta function are complex number whose real part is 1/2, like this. How to prove this? Okay, because of it related to zeta function, we have to recall zeta function again, or we have to write something that related to zeta function, right? and we have to know what necessary condition for zeta function satisfied. I mean, we have to know, we have to understand. Okay, proof. Let me show you here proof. We have zeta function or Riemann zeta function, zeta s. Yeah, zeta s. Zeta s equal to what? Equal to the sum. Yeah, as I told you, I will call it in short like sigma. The sum and from 1 to plus infinity. Yeah, 1 over n power s all equal to the sum and equal to 1 to infinity and power negative s. And for this zeta function, the s is any complex number s is different from 1. This is the condition of zeta function. So to prove the Riemann hypothesis, I will let s be any complex number, and I will find the real part and imaginary part of s. And at that time, if I find the real part and imaginary part of s, that I let s be the non-trivial 0, I will show that the real part of s is equal to 1 over 2, and b is any real number that I will show you in a little bit time. Okay, so let's s equal to a plus b I is imaginary unit. Yeah. So because of we let s equal to this, but what is s? Let s equal to a plus ib, b what? A non-trivial, I mean a general non-trivial 0 or zeta. Yeah. Non-trivial 0 of zeta function, or we can say in short zeta. Yeah, zeta function. And because s is non-trivial 0 of zeta function, so s is not trivial 0. We get this. And also s is different from 1. So since s different from 1, why? Because the condition or the necessary condition of zeta function, s has to be satisfied as different from 1. Yeah. And because s is not trivial 0, so s is not equal to any trivial 0 of zeta. As I told you, trivial 0 equal to the negative integer. Yeah, so I can say s different from to t less than or equal to negative 1, and t belongs to z. Here, b belongs to z. Set of integers z, right? And from this, we can get the condition of a here and b. So, in order to get s is not equal to 1, we divide into two cases. Case for b equal to 0 and b is not equal to 0. So first, if b is not equal to 0, so s exactly it's not equal to 1 or it's not equal to 2t, which is the negative integer, right? So this is when you put b is not equal to 0, you get these two conditions satisfied, right? Yeah. Or b equal to 0. B equal to 0, you get what? B equal to 0, so a cannot be 1 or a cannot be 2t. Yeah. If b equal to 0, then and a is not equal to 1. Or, yeah, b equal to 0 and a different from 2t, where t belong to z, yeah, and t less than or equal to negative 1. This is the necessary condition of a and b, which are the real part and imaginary part of the non-trivial 0s, right? So I will use this condition to prove my Riemann hypothesis also. Okay, let's start together to prove Riemann hypothesis. We continue here. Okay, like I say here, we have zeta s and Riemann zeta function equal to what? Equal to sigma k of n from 1 to plus infinity 1 over n power s, or equal to sigma n from 1 to plus infinity n power s. And this I just replace s by a plus ib, so I get sigma n from 1 plus infinity, and this one I get n power negative a negative ib. I replace s here by a plus ib, so we multiply by negative 1, here you get minus a minus ib. And this one I use the exponential law, so you get equal to the sigma, yeah, n from 1 plus infinity, and then this one n power minus a multiplied by n power minus ib, yeah, this one. So it's continue here. It's equal to what? Here I can say sigma n from 1 to plus infinity, and then n power negative a, I get 1 over n power a, like this. And this one I get, yeah, use the exponential law, n power negative ib, I get e power, yeah, natural log here, yeah, natural log, we can say ln here, natural log of what? Of n power negative what? Negative ib. You got it? Yeah. And next, what do we get from this? What do we get? Okay. Minus ib is also complex number. So what do I get here? N power minus ib. So you get from this, you can get like sigma here, n from 1 to plus infinity here, and 1 over n power a, I can say 1 over n all power a, like this, right? Okay, and from this I get e multiply e here I refer to Julia number, e multiply e power I b multiplied by natural log of n, right? Okay, so start here.